Hello, everyone. Welcome to the Wednesday Security Seminar yet again. It is my distinct pleasure to introduce someone who is really a legend in the field of cybersecurity to the people who've been working in it for a while. He's got a history that goes back in this field about 50 years, really. Started in MITRE Corporation, then went to Digital Equipment Corporation and participated in the development of one of the first A1 secure systems under the old Orange Book series, the Rainbow series. After more time at MITRE and Trusted Information Systems, he went to Microsoft, where he was partner director of software security and helped lead the development of the software security lifecycle, software development lifecycle there at Microsoft. After doing a lot of work there, and I'll say that Microsoft kernel went from being one of the least trustworthy kernels to one of the most under his supervision. He retired a few years ago and is now the executive director of SAFECode. So he has a long history of experience building very secure systems and helping to secure systems that weren't quite as secure. And along the way, learned some lessons, and he's going to share those with us today. So Steve, thank you so much. Take it away.
Thank you, Spaff. Thank you, Spaff. So you sort of hinted at some of the things that that I was going to introduce in the first slide. As you said, I actually started working on computer security, as it was called then, in 1970, and I never quite got out of it. Actually, my boss at MITRE said, "We've got this problem." And I said, "Well, my degree's in civil engineering. I don't know anything about the, computer science, or, you're probably talking about proving programs. I don't know anything about that. You ought to get somebody with the right background." And he said, "Well, that makes sense to me, but I don't have anybody to put on that assignment right now. Why don't you just see what you can do until we can hire somebody with the right background?" And that was in 1970, and I never quite got out. Lot of interim steps, which Spaff alluded to, and which I'll talk a little more about in the following slide. As Spaff said, I joined Microsoft in '99, was primarily responsible for the creation of the security development lifecycle process that did make a difference in the way we looked at building secure systems, and retired from Microsoft in 15, started working at SAFECode in 16. SAFECode is a small nonprofit. Members are companies in the industry. They all have secure development processes similar to the security development lifecycle. And so as executive director, I try to sort of provide strategic and technical guidance on basis. This presentation isn't about SDL or things that I've normally given talks about a lot. Instead, more for sort of new folks in the field, or folks who are trying to learn some of the background or history or other considerations. It's focused on mistakes, things that I did that I wish I hadn't done, or wish I hadn't done as much of over the last 50 years. And maybe that tells you something about how to think about what you're facing and hearing. I'll wrap it up with some lessons learned and suggestions, and then I hope I hope I'll do that in time to let you get on with your day, and consistent with the schedule for the class. So relevant career history, as as Spaff said, I was with the MITRE Corporation. Actually, I was with MITRE from 70 to 81, 69 to 81. So these are the times I was working on primarily on security. And that was at MITRE just from 70 to 76. I did other things before and after that time. 81 to 92 with Digital Equipment Corporation. Company doesn't exist anymore. Mini computers, super mini computers. The industry took a turn to PCs. Digital didn't, and that was the end of digital. Trusted Information Systems, largely a government research contractor. We built a commercial business, went public. I was with the company in 87, got bought out by a bigger company in the security business in 98. And then Microsoft lives on. I talked to those folks. They're a SAFECode member, but I was there just from 99 to 2015. I joined them to run the Security Response Center, which was the organization that dealt with externally discovered holes in Microsoft products. And I used to joke that when I joined them in 1999, I was 20 years old. And you're supposed to look at my appearance now, add 20 to the time since I joined them in 99, and laugh at the aging effects of working for Microsoft on vulnerability response back in the day. But in fact, it was an interesting adventure. Not really primary subject of this talk. So let's talk about some of the mistakes. Mistake one is the Bell-LaPadula model. I don't know whether you've studied multi-level security, whether you've studied security models, but Bell-LaPadula was one of the earliest security models for dealing with classified information. It was explicitly driven by the objective of meeting the Defense Department's needs for what they called multi-level security. I want a system that can handle both top secret information, which is very sensitive, can cause damage to the national security, and unclassified information, which is public or close to it. And I want users who are only authorized for unclassified information to darn sure not be able to access classified information, not be able to access top secret information. And so our first challenge when we started thinking about that requirement was to figure out, well, okay, what does that mean in precise terms that we could implement with a computer system? And a couple of really very good mathematicians named David Bell and Len LaPadula, both of whom are now members of the National Cybersecurity Hall of Fame, tackled that problem, and they came up with a mathematical model whose effects I've tried to illustrate with the graphic here. You have top secret files, you have unclassified files, you have top secret cleared user or process and an unclassified user or process. And the rules of the model, I won't give you the mathematics, are that the unclassified user can read or write the unclassified file, and the top secret user or process can read or write the top secret, but can only read the unclassified file. And so that gives you sharing of information that's consistent with the DoD model for information security. And it also has the effect, which is important in building a real computer system, that even if the top secret user or top secret process is running a Trojan horse, some very untrustworthy software, it can't take the top secret and disclose it down into an unclassified file and thence out the internet or out the door in somebody's pocket and do harm to national security. So at the time, that was the requirement set, and the model was a major breakthrough. It wasn't the first security model that attempted to address multi-level security, but it was the first that was resistant at a model level to this threat from Trojan horse programs. And if you built a system right that enforced that model, it was pretty useful and a pretty significant breakthrough. And we actually built it into a time-shared Multics system that was used at an Air Force data center in the Pentagon. And I believe there were other Multics systems in the Defense Department that probably used the model as well. And it worked, quote, okay there. The users were happy with it. They shared information, they shared programs, and it was usable in that context of a 70s time sharing system. I believed, as I say here, that it was a general solution for multi-level security. You know, if you've got a system, if you've got a requirement for a system that's going to handle classified information, Bell LaPadula's your answer. Turned out that Bell LaPadula wasn't your answer. In practice, there were too many reasons to violate the requirements of the model. What's an example? Well, I'm logged in at top secret, cruising along, and I get an unclassified email, and I want to reply to it. Okay, so now I have to log out, log in as an unclassified user, and then I can reply. But from top secret, I can compose a reply, but when I click send back to the unclassified user, the model enforcement is going to say, nope, you can't do that. And in the real world, what we did was wind up inventing pop-up fatigue. Anybody remember Windows Vista and the allow or deny permission when people wanted to install new software? Well, that was a very similar model called the BIBA integrity model, working its way with a highly interactive system with real world users. I remember seeing a mail system that was running the Bell LaPadula model where we had users just sort of constantly clicking OK, clicking OK, clicking OK. And, and that clicking OK says there's not actually any top secret information going down there. And, and if people have to do that once a minute or more often, there's no way they're exercising judgment. They're just clicking OK. So good idea, didn't stand, couldn't really withstand interaction with the real world. Mistake 2 was kind of a compound on Bell LaPadula. The Defense Department, I think Spaff referred to the Orange Book, the Defense Department liked Bell and LaPadula, and they built it as a core tenet of their Orange Book security evaluation criteria of the 1980s. And so there were various levels of systems that you could build depending on how much effort you put into enforcing the rules and making the system secure. At the highest level, you had to implement the Bell LaPadula model, and you had to do that with high assurance, formal specification, formal verification. I sold Digital Equipment Corporation on the proposition that we needed to be in that security market. And so what we should do was build an A1 system, a system that was as secure as DoD knew how to evaluate. And we actually built a virtual machine monitor for the VAX architecture super mini computers that implemented Padula, used a virtual machine monitor architecture to minimize the amount of software that we had to trust. And still, because it was a VMM, still provided compatibility with the existing user code and operating systems that ran on the VAX architecture. So here's a little sketch from a paper. You've got multiple virtual machines, one at top secret, one at secret, one at unclassified, some of them running VAX, VMS, some of them running the Ultrix operating system, which was DEX Unix. We got that for free. The minimal mechanism was all in the VMM, the virtual machine monitor security kernel. Users connected through that. And if you had to, if you had to switch from top secret to unclassified, we gave them an easy way to do that. So it was pretty cool. We built it. We got it to the point where we were actually able to dog food it, to self-host it in our development group, and we were doing the SVS development on SVS systems, which is sort of a test of whether you've got a system or not. And that was all pretty cool. But there were some real world problems. As I've shown on this slide, the development wasn't easy. We were trying to minimize the trusted code. The performance, VMM performance is a potential problem in any case. And the VAX wasn't really designed to be virtual machine monitor friendly. I think that systems like VMware today offer, implement some technologies that might either have been not viable with machines as slow as the VAXs were, or we just didn't have them. And then the performance, the security evaluation process for our secure system was what I would call adversarial. The evaluation people got points for for making us fail, not for making us succeed. And so that was interesting. All those things said, we ran well behind schedule. I don't think we ran over budget because we always had trouble getting enough people, just hiring enough people to work on the thing. But we eventually got the system done enough to be in beta test. And some of the users liked it, but in general, users had moved on. They wanted PCs. This was the late 80s. They wanted PCs. They wanted networks. They wanted graphical user interfaces. And what we had was a terminal time sharing system that was really worked really well, compatible with the technologies that you had in the mid 80s. And so, my characterization is nobody wanted a system that secure, or more accurately, nobody wanted to pay in performance and usability the price of a system that's secure. And I wound up canceling the project in 1990, one of the sadder days of my life, but clearly the right decision, because if we had continued to build it, we wouldn't have sold enough, and we would have lost a ton of money trying to enhance it and support it over the years. I can answer more questions about the cancellation decision and what I mean by losing more money when we get to the end, if you're interested. So that was a mistake too. Sort of closely linked to the Padula mistake and doubling down to make a bigger and more expensive mistake. After another another product of that same DEC era was what we called the Desnet, the Digital Ethernet Secure Network Controller. DEC had adopted Ethernet in the mid 80s. And I assume you've studied Ethernet. You know, it's basically a single shared medium, and anybody can transmit or receive on that medium. And without encryption, you know, anybody can hear what anybody else is saying, or anybody can spoof what anybody else claims to be saying. Our DEC product family at the time used at least a couple of transport protocols. One of them was DECnet, which was DEC's proprietary networking protocol for connecting its own products together. Another was LAT, which stood for Local Area Terminal Protocol, and it was used to connect servers that where users dialed in or connected with dumb terminals, connect the terminal servers to time-shared mini computers. And so we had multiple transport protocols running over Ethernet. We obviously wanted a security solution, and what we came up with was Desnet. And Desnet, this is a drawing from a patent, looked like this. You had encryption controller boxes, which weighed about 20 pounds and supported 4 nodes each. And each of them had enough logic to keep the individual nodes separated. And so information would flow. Lost the cursor. All right. Well, information would flow from an end node, say A1, up through encryption controller A, then through the transceiver and onto the network, down to encryption controller N, and then back to node N1, where the encryption controller N would decrypt it, and it would flow back in plain text to node N1. And the I think it was 4 end nodes per controller, were a way of offsetting the cost of building this thing in discrete logic. We also built a key distribution center, which was basically the same controller hardware with slightly different software and data, and it would establish authorized and keyed connections that allowed, say, A1 to talk to N8 if that was what it wanted to do. And so it was a pretty nice solution, and it had some appeal. But there's always a but. And in the Desnet case, it had both what Salter would refer to as technological and fundamental problems. The hardware was too costly, and we had performance problems. And so that was our technological problem. The fundamental problem was that it was a sort of a solution to the wrong problem. The DECnet was going away. Terminal concentrators were going away. All the other vendor proprietary networking protocols were going away, and the world was moving to Internet Protocol. And the right answer would have been a software implementation of end-to-end encryption at the IP layer, which would have been great. But if you said TCP/IP within the bounds of Digital Equipment Corporation, that was what you might think of as a career-limiting move. And so we really had to do something that would work with the then DEC proprietary protocols. The Desnet IP, and people did in fact use it to secure IP networks, but it wasn't a real success because it was too expensive and had a lot, basically the protocol independence drove a solution that just wasn't the right one for the time. So that was mistake 3. By the time that SVS was canceled and the Desnet actually made it to market, digital as a whole was going into a decline, caused primarily by their, I guess I would say, their failure to pick up on the PC revolution, failure to pick up on graphic workstations quickly enough, and maybe their failure to get on board with TCP/IP networking quickly enough. And so I left DEC in 92, worked for a couple of years with MITRE again, and then joined Trusted Information Systems in 94. Trusted Information Systems had built, with DARPA funding, an application firewall toolkit. It was people didn't refer to open source back that long ago, but it was basically an open source deliverable that we put up on the web and anybody could download and use to implement a firewall for their own use. We retained the rights to productize Gauntlet, the firewall toolkit, and our product was called Gauntlet, and it was the firewall toolkit code plus a little management software. And at various points, we actually packaged it with hardware, so you could buy a box with the firewall software preloaded, and somebody would come out and configure it for your installation, and it would be up and running. It was reasonably successful, but in the process of running that product, I made a couple of mistakes, and they were both connected to, sort of the fundamental principles of having complete mediation, and especially minimal trusted code. We thought that if you didn't have much software, you couldn't make many mistakes, and so that would lead to a secure solution. And I made 2 mistakes, both connected to the sort of minimization. One of them is I didn't invest soon enough or deeply enough in a fancy management graphical user interface. You had to go in and configure the Gauntlet firewall by building ASCII text tables of who could talk to who and what node was where, what the IP addresses were, and users didn't like that. They wanted to point and click even by 1994, 95, and we didn't have enough of that capability soon enough. Specifically, when we ported, the Gauntlet ran on BSD Unix. When we ported it to NT, there was one feature called network transparency that would basically let the system detect connectivity without much user intervention, without configuration. And getting that on the Unix systems was pretty simple. Getting it into on NT at that time would have required a complex hack that we were loath to do, and we went back and forth arguing with Microsoft about giving us an API to make that function simpler. They didn't do it in the time in the time frame we needed, and so we went with manual configuration rather than trying to build that hack. Those 2 things sort of reduced the usability and acceptability of Gauntlet, and we probably weren't enough of a marketing company anyway. But the bottom line was that Checkpoint Firewall 1, which I think is probably still sold, had a really slick graphics interface, had better NT support, and they ate our lunch. The company was sold about a year after I left, and the product rattled around the industry for probably 10 more years. And then I think it's now disappeared from view. So sad story. no excuses, or maybe prioritizing a set of security principles at the expense of the market was in retrospect not the right thing to do. Another sort of interesting mistake in today's world had to do with what was called a key escrow system. I don't know whether you've followed the debates among FBI, Justice Department, and so on, and the civil liberties and internet community about law enforcement access to encrypted information. But that debate has been around for almost 30 years now. And it started with a system called Clipper, which was actually it was a secure voice device that sat between a telephone and the wire. No, it sat between telephone handset and the telephone, and provided encryption, but did it in such a way that there was an extra key involved that was held by a couple of government agencies and could be recovered to break your encrypted communications if the government decided it needed to do that. And that was controversial. TIS was pro-crypto export. They thought that people should have access to encryption worldwide. Thought that the export controls were bad. Thought that the Clipper chip was bad. And our CEO, the late Steve Walker, asked me to invent a way to invalidate a couple of government claims, namely that the only way to meet their requirements was to use a non-public algorithm implemented in hardware, and to use those were the requirements: the non-public algorithm and a hardware implementation. And so I came up with a solution that could be implemented in software, met the stated government requirements, and still provided key escrow access and a level of security for users within that context. When that happened, when I came up with that solution, our CEO, who had previously been pro-crypto export opposed to the Clipper chip, decided that, hey, maybe there's a commercial market for a key escrow solution. We'll sell it. And so we invested significant resources in building and selling a key escrow solution. Actually, one of the versions was added to the Gauntlet firewall with the aim of meeting customers' needs for being able to export encryption and still having government license, because the government could intercept. There's more to the story than that, but I think that's enough to give you a sense of what happened. And in the ensuing scuffle, the investment distracted the company from the Gauntlet business, so we didn't invest as much in graphical user interface or NT implementation as we should have. And then after arguments back and forth with civil liberties groups in the industry and so on, the government abandoned the key escrow mandate. And that was, although we claimed that there were commercial needs for key escrow, the fact of the matter is that, once the government abandoned the key escrow mandate, all the customers and resellers abandoned the key escrow mandate, and we were left with 6 patents, but no income. So a lesson learned there in the process. Final mistake is, I think of as much more recent. This is the only mistake that I'm going to associate with Microsoft. In 2002, we after some real disasters, or at least major embarrassments associated with the security of Windows software, we took the entire Windows division and stood them down, gave them all training on what we understood then to be secure development. Then we trained them for a half a day. Every engineer got a half-day training. There were about 8,500 engineers, sent them off to try to improve the security of the product. And a lot of that worked very well. But one of the things that our training tried to do was to teach our product engineers to think like hackers and find vulnerabilities and invent attacks. And it turned out that a few of those 8,500 could, but most couldn't. And so our investment in teaching them to think like a hacker, to invent new vulnerabilities from scratch, really didn't work. Fortunately, we had other things like running static analysis tools, looking for specific code patterns that we taught them, building specific kinds of tests, looking at specific configurations, doing what we call threat modeling. That's another story. Those did work. So overall, there were certainly benefits from it, but we assumed that we could teach all our developers to think like hackers, and they'd all find new classes of vulnerabilities by understanding what a vulnerability was, and that just didn't pay off. We didn't get a payoff in vulnerabilities that corresponded to the effort people should put on it, and they should have been putting more effort on code reviews for known bad patterns, either manually or with the static analysis tools. So another lesson learned. So here's sort of the bottom line that I've taken away from those 50 or so years of more mistakes. I'm not sure if more mistakes than I care to admit. I guess I just admitted them. The customer's right, even if you think the customer's wrong from a security fundamentals or what he or she should be wanting, the customer gets to decide whether they use your technology or not, and that turns out to be really, really important. I mean, it sounds sort of stupid to say, but when you're a security person, you think security is the thing that it's about, and if the customer doesn't agree and you can't convince them, then that's not going to end well for you. Usability is important. I know people spend a lot of time now on trust user experience and secure usability, and that's a good thing. It's something that I think the security field came to late and is very important. Security isn't everything. I think I just said that in talking about customers. It's a balance. Something that I've learned a couple of times, both with the Orange Book and with the key escrow exercise, is that the government is perfectly capable of promising you that they're going to go in a certain direction and that their standards and requirements are going to create a market. And the government is also perfectly capable of changing its mind or backing off or granting waivers. So you really want to think carefully before you decide that a government security requirement is going to create a market that you're going to fulfill. That's not guidance for government contractors, obviously. If they're paying you a contract, they're paying you a contract. But if you're trying to build a commercial product based on a government mandate, that may or may not end well. And you need to really think, how am I going to sell this, even if the government changes its mind. Time to market is better than perfect. If you fool with security long enough, the market may have moved on, and you may have the best buggy whip in Kansas or something. And then finally, think about what your organization norms are telling you as you're trying to build a solution. The norm at Digital Equipment was DECnet and LAT, their proprietary protocols. And the reality was we would have been better off with IP. The norm at TIS was small, small, simple, minimal code, trust at all cost. And we would have been better off building a hack for transparent firewall access and building a big complex GUI that people liked and would use to configure their firewalls. So a lot of challenges as you're planning and strategizing to do something that is successful. And my definition of success is really something that people will use that will help them get better security, not something perfect that maybe nobody wants. So with that, I think I'm a little longer than I had hoped to be, but got some time for questions. And SPAF said that it's the last slot, or you don't have to walk to your next class. So if we stop now, let's take some questions.
Can you see the question and answer window there, Steve, or would you like?
I need to open it. Okay. Okay, somebody asks I'll do these unless we get overwhelmed, at which point I'll punt it to you folks. How does Bella Padula deal with compartments? Those technically would be peer levels above top secret. It's a lattice is the answer. So you deal with you deal with the security levels as as integers with a less than greater than comparison, and you deal with compartments as binary attributes, they're there or not, and you deal with them by set inclusion. So top secret apple banana dominates secret banana. Top secret apple banana and secret cherry are incomparable. Is that an answer? I don't know whether people can talk back or whether they have to type their questions. But if you can talk and you have want follow up, either type or holler.
Thank you. I was just typing the question, but yeah. So basically, you're saying that if I needed to move a piece or copy or make a piece of information available in more than one compartment, that would be equivalent to applying an additional label to it, right? The
compartments are orthogonal. Compartments are orthogonal to the security levels, and they're a set of individual attributes, and you can to read a document or an object with compartments associated with it, you have to have all those compartments on your process.
Yeah, and basically, if I needed to have information from one compartment accessible in another compartment, that would require an external. It would not be the user doing that, but it would be an external force that would basically change the label or add an additional label, right?
Yeah, right. If you know, let's say if I have top secret apple banana, and I want to share information derived from that with somebody who only has access to secret and cherry, you know, that's a case that I was talking about, you know, when I was talking about the model. You know, you have to drill a hole in the model somehow to get that information through.
Yep. Got it. Thank you.
Okay. Other questions? Let's see there. I've got, oh, okay. Yeah, all right. Yeah, somebody, Bill Malik, who is a name I remember from the past. In a sense, the government didn't abandon the key escrow initiative so much as redirect the funding to crypto AG. That's a different story, Bill. Other questions?
Well, I'll pop in here and ask if you could say a couple words about what SAFECode is doing now and what you're enabling in the community, because you've retired, but you've not. You're still at it. So.
Okay, so SAFECode is an organization been around for about 15 years, and we really do two things at this point. One of them is that we have our members work together to share best practices and techniques for building software securely. You know, what kind of testing approaches, what kind of training, you know, can we work together to build developer training that then we can then use across the member organizations. And the other thing that we do, pretty closely coupled, is that a lot of what we do is aimed not only for sharing among the members, but we make that public. So if you go to the SAFECode website, there's a series of blog posts that are basically an introduction and recommendations and trade-offs about using fuzzing tools to improve product security. There's another series that's underway. As a matter of fact, I'm delinquent reviewing the next couple of posts about the transition to post-quantum encryption. There's a series that's going on about developer training. What kind of training do developers need, and how do you get and deliver that? There's a series from about a year ago about organizing security champions, basically people in a product group who are the security advocates for building products securely. So a lot of different topics, all associated with building software securely, and most of them shared with the community. Basically anybody who wants to download them or read them or use them.
That's great. And I hope some of the listeners, both in person now and for the recording, do check out the site. There is some really valuable information there.
Yeah, it's lots of information. Look at the blog. Look at the documents. There are a couple of longer documents. You know, supply chains, another topic. There's a fundamental practices for secure development that folks may find interesting, just in terms of, you know, sort of what the SDL approach to secure development has evolved into.
Well, I'm not seeing any new questions open up here, and so we're at close to the end time, and no questions. So Steve, thank you so much for taking time to speak to us today. And I hope maybe we can get you back on another occasion, maybe even in person. And that would be great fun to hear some more about lessons learned.
Yeah, I'd be happy. I mean, the lessons learned talk is sort of more historical. I'd be happy to talk about, sort of as well about what works and doesn't in secure development, because I think that's possibly more, more relevant to today and the way people actually create and operate security programs. Thank you for inviting me, SPAF. Thank you to the folks at CERIAS, and looking forward to seeing you again.
All right. All right, everybody. Thank you for attending, and stay safe. Bye for now.
Thank you all. Bye-bye.